Check it out now, y'all.
NanoHub U, online instruction.
Hi, welcome back. This particular lecture, we're going to review what you hopefully already have learned about Maxwell's electromagnetic waves. And in particular, we're going to focus on energy transport, radiation, pressure, and interference, and remind you of the standard results that you can find in all the textbooks when these topics are discussed. So again, this is more of a review lecture. We're trying to set up a discussion of some experiments that were done in the late 1800s. The experiments were compared to these standard results, and the comparison was pretty bad, right? The experiments didn't agree with expectations. And in order to sort that problem out, everyone had to start rethinking how matter interacts with electromagnetic radiation, and that turns out to be the key to the development of modern physics. So to begin with, let me remind you of Maxwell's equations. These were 4 equations that were written down in 1864, and they attempted to summarize all the important properties of electric and magnetic fields that had been discovered up until that point in time. It's simple to draw pictures that sort of schematically illustrate what these 4 equations are attempting to convey, and that's what I've done in this slide. Right, there's one equation that basically says electric field lines diverge from a point charge. There's another equation that says magnetic lines, in contrast to electric field lines, magnetic field lines are continuous, right? They close back on themselves. There's an equation that describes Faraday's very famous experiment where he pushes a magnet through a loop of wire, and in the process of pushing the magnet through the loop of wire, a current I is induced in that loop, right? So that's one of Maxwell's equations. And then the 4th equation relates a current flowing through a wire to the magnetic field that's produced by that current. And those magnetic field lines, of course, are continuous, and they curl concentrically around the wire. So in pictorial terms, these are the important features that Maxwell's equations try to capture. The way they do that is in terms of equations that can either be written in integral or differential form. I don't know whether you have, I don't know which form of these equations you have studied, but the case I want to make here is that there's basically 2 proportionality constants that appear in these equations, right? One is this proportionality constant epsilon naught. This refers to the permittivity of free space or a vacuum. And the other constant is this permeability of free space, mu naught. And these proportionality constants basically link up or convert the charged, in this case, the charge density rho is converted to a divergence of the electric field E, and the proportionality constant is this parameter epsilon 0. Down here, the current density J is converted to the curl of the magnetic field B. The proportionality constant is given by this quantity mu 0, right? So these 2 proportionality constants turn out to play an important role in the development of electromagnetic waves. So what Maxwell was able to show was he was able to show that if you take these 4 equations and you manipulate them, you can get 2 equations, one equation for the electric field, another equation for the magnetic field. And these 2 derived equations have the same form as the wave equation that we discussed in the prior lecture. And this led Maxwell to hypothesize that there could be something called an electromagnetic wave. And that electromagnetic wave can be sketched out, and it has the form that we show in this picture. It's an oscillation of an electric field, and at right angles an oscillation of the magnetic field. The electric field and magnetic field are synced in phase, so whenever the electric field has a maximum value, the magnetic field also has a maximum value. Whenever the electric field goes to zero, where there's a node in the electric field, the magnetic field also goes to zero. And this disturbance of electric and magnetic fields moves in space with a velocity v that's designated by this special value c, where c is referred to as the speed of the electromagnetic wave. Now, because the wave is because these disturbances of electric and magnetic field obey the wave equation, right? There's a fundamental relationship between the frequency of the wavelength of the wave, and the speed of the wave c. And that relationship should be familiar to you from our review of waves on a string in the previous lecture, right? The same sort of equation resulted, except in that case, the speed of the wave was designated by v. Here, the speed of an electromagnetic wave is designated by this constant c. So how fast can these electromagnetic waves move? Well, Maxwell was able to show that the speed or the velocity of these electromagnetic waves was in fact related to 1 over the square root of the product of those two proportionality constants that we discussed in the previous slide. So you take this proportionality constant epsilon naught, multiply it by mu naught, take the square root, take 1 over that value, and what you find that the speed of this wave is about 3 times 10 to the 8th meters per second. And that's fixed, it's constant, because it's determined by these two constants here, right? So the speed here is not variable. It can't be adjusted in free space. It's a constant value for all frequencies and all wavelengths. The other thing that Maxwell was able to show was he was able to show that the proportionality, or that the ratio between the E field and the B field, was just equal to the speed of the electromagnetic wave. So E over B is equal to C. That's another result that we're going to use in the lecture in the slides that follow. So this very simple equation has profound consequences, right? It basically says there are a large range of frequencies and a large range of wavelengths which when multiplied together equal this constant C. And this gives rise to the idea of an electromagnetic spectrum, where the electromagnetic spectrum is comprised of a huge range of frequencies and wavelengths, such that for any given frequency and the corresponding wavelength, right, the product of the frequency times the wavelength just equals the speed of the electromagnetic wave c. When Maxwell made these predictions in 1864, it was not clear how to produce these electromagnetic waves. In fact, it took about 30 years before electromagnetic waves were successfully launched or generated and then detected. This was done by Hertz in the 1890s. But it became pretty clear early on that the visible region of the electromagnetic spectrum is what we refer to colloquially as light, right? Light is an electromagnetic wave. And our eyes are sensitive to the different colors of light. The different colors of light are just represented by the different wavelengths and frequencies of the electromagnetic radiation. So, for instance, I just provide this convenient table here that tells you what the frequencies and wavelengths of red to violet light are. They span a range in the electromagnetic spectrum. So, many different types of electromagnetic waves are possible, different frequencies and different wavelengths. Technology has come to use these different regimes of the electromagnetic spectrum for different purposes, so it's not terribly surprising. The message that I want to convey is that from the earliest prediction of these electromagnetic waves up until the 1890s, there was a lot of work that was done to predict properties of these electromagnetic waves. And in the remainder of this lecture, I'd like to focus on the energy transport. In other words, how much energy is transported by these waves as they move through space. And the answer to that question involves a number of concepts which are referred to as intensity. There's the power of an electromagnetic wave. There's the energy density that an electromagnetic wave possesses. There's actually momentum transfer in an electromagnetic wave, and there's also radiation pressure that's exerted by an electromagnetic wave. And all of these properties can be derived from considerations based on Maxwell's equations. And in order for you to understand the remaining lectures that will be given in this first week of the semester, it's important for you to have some understanding of what these words mean and what the predictions of Maxwell's equations were for these various quantities. So let me start off by defining something called the Poynting vector. The Poynting vector is this quantity S in this equation. It's defined as the cross product of the E field and the B field in an electromagnetic wave. S points in the direction that the electromagnetic wave moves in space, and S basically tells you the instantaneous power per unit area that's transported by an electromagnetic wave at a particular point in space at a particular time. So the notation here is that because E and B are perpendicular to one another in this electromagnetic wave, the cross product is very simple. It's just the magnitude of E times the magnitude of B. I indicate E and B can depend on time by explicitly indicating that here. So this means you tell me the time, and I can somehow calculate what E is at that time and what B is at that time. I multiply those two quantities together, divide by this constant mu naught, and that tells me what the magnitude of the Poynting vector is at that particular instant in time. This Poynting vector can be written in a number of different ways, and in particular, it's often written in terms of the instantaneous value of the electric field in the electromagnetic wave. Now, the trouble is these electromagnetic waves oscillate so quickly that it's difficult to instantaneously measure the power in the electromagnetic wave at a particular point in time. This was certainly true in the 1890s, and it's little has changed up until the present, right? We don't have electronics that are fast enough often to monitor this instantaneous power. So what we do is we replace the instantaneous value of the electric field squared by the average value of the electric field squared. And since the electric field is specified by a sinusoidal wave, right, the average value of the instantaneous electric field averaged over one period is just equal to the amplitude E0 squared divided by 2. So this follows directly from the fact that the electric field in an electromagnetic wave varies sinusoidally with time. And this quantity E0 squared over 2 is often referred to as the RMS value of the electric field. So depending on which textbook you learned your electricity and magnetism from, right, you'll have these two different definitions for the average value of the Poynting vector. Right, the Poynting vector has units of watts per meter squared. So what it's basically telling you is if you have an area that's 1 square meter with an electromagnetic wave with a certain average Poynting vector incident on that 1 square meter, you're delivering so many watts of power to that square meter every second. Now the time average value of S is often referred to as the intensity of the electromagnetic wave, and the intensity is referred to as capital I. So there are different expressions for the intensity of an electromagnetic wave that can be written down. The intensity can be expressed either in terms of the electric field component E or the magnetic field component B, because the electric field and the magnetic field components are related to the speed of the electromagnetic wave C by this simple relationship. So you'll, depending again on which textbook you read or what you look at, you'll see different expressions for the intensity of the time averaged intensity of an electromagnetic wave represented by this quantity I. Now, I is something that you can directly measure. You can go to Walmart and you can buy yourself a power meter and you can measure the intensity of an electromagnetic wave in watts per square meter, right? From that measured quantity, you can derive a variety of different properties of interest, right? Just by using some very simple theory. So for instance, you can tell the watts, the power transmitted by an electromagnetic wave, if you know the intensity of the electromagnetic wave and if you know the area A that electromagnetic wave illuminates, right? So the power carried in an electromagnetic wave is just the product of the intensity times the area which that electromagnetic wave falls upon. There's also a question about how much energy is transported by an electromagnetic wave in a time delta t, right? That energy is given the symbol capital U. We use capital U because the symbol capital E is already reserved for electric fields E. So when we deal with energies in electromagnetic waves, we tend to deal with this quantity capital U. And the energy carried by a wave is just the power in that wave times the time delta t that wave is illuminating the surface. So the energy U is equal to the intensity I times the area A illuminated times the time interval delta t that illumination is turned on. And the last quantity that's of fundamental interest is the definition of something called the energy density of an electromagnetic wave. Now, the energy density is basically telling you how much energy is stored in a certain volume of space that's filled up with this electromagnetic wave. So the energy density is the units of energy density are joules per cubic meter. And it turns out that the total energy density in an electromagnetic wave is going to be equal to the intensity of that wave divided by the speed of the wave c. So we'll derive this equation on the next slide. It turns out it's a fundamental property of an electromagnetic radiation, and it's something that can be inferred from measurements, and it's also something that can be calculated from first principles. So it's a useful quantity to know about. So the way you think about energy densities in electromagnetic waves is sketched out in this simple conceptual diagram. What you have is you have a screen with a hole cut in the screen. The area of the hole is A. You illuminate that hole in the screen with radiation that has an intensity I, and you illuminate that hole over a time interval delta t. So in that time delta t, the electromagnetic radiation travels the distance c times delta t, right? And so there's a volume of space with a length c delta t, cross-sectional area A, and that volume of space contains all the energy that passed through this hole in that time interval delta t. So you can define this energy density U, small u, as the total energy passing through that hole divided by the volume of that cylinder. And when you work through the arithmetic, you end up with an expression for this energy density U in terms of the intensity I and the speed of the electromagnetic wave c, right? And that has units of joules per cubic meter. So this is something that you calculate. This is something that you measure. So you measure I, you know C, and you can infer U total. It also turns out that this electromagnetic wave exerts a force on an absorber, right? Now, this is not obvious to begin with, but if you sit down and think about it, it becomes clear. And the reason a force is exerted on the absorber is because there's an electric field that varies in time that's perpendicular to a magnetic field that varies in time. So any charges in this absorber will experience a force produced by this electric field. That force will cause the charge to oscillate back and forth in time, right? So if the charge is a positive charge, it'll follow the direction of the electric field. If it's a negative charge, it'll move in a direction opposite to the electric field. Okay, so this electric field imparts a velocity to the charge, and anytime you have a charged particle with a velocity v at right angles to a magnetic field B, you exert a Lorentz force on that charged particle, and that Lorentz force is given by this expression QV cross B down here. So in general, this force is going to cause a change in momentum of the charged particles with respect to time. Change in momentum with respect to time can be linked back to mass times an acceleration, right? So if we can calculate the forces by knowing what the strength of the electric and magnetic fields are, then we can calculate the change in momentum that those particles experience, and that change in momentum is then going to exert a net force on the absorber. You can work all that out, okay? You can work all that out, and I do that in this slide. Here I just show what the change in momentum of the electromagnetic wave imparts to the absorber. It turns out it's proportional to the intensity I, it's proportional to the cross-sectional area A. It depends on the length of time that electromagnetic wave illuminates the absorber, and it's inverse with the speed of the electromagnetic radiation. And if there's a change in momentum, then the change in momentum divided by time means that there's a radiation force exerted on the absorber. The radiation force turns out to be just the intensity I times the cross-sectional area A divided by C. And if you divide that radiation force by the area A, which is what I do here, then you end up with a radiation pressure that the electromagnetic wave exerts on that absorber, and that radiation pressure is just the intensity I divided by the speed of the electromagnetic wave. So what I hope you see from this diagram is that this quantity I keeps popping up in all these definitions of forces and pressures, radiation pressures, that this electromagnetic radiation exerts on a solid object. And that's going to become important in the next lecture to understand that connection. Another property of electromagnetic waves is that they can experience interference effects. And this interference is a property that's really unique to waves. And I like to introduce it, or I like to discuss it by just asking what happens when two waves collide, right? That's a fair question. And the answer is that when two waves collide, they combine, right? According to this very famous principle of superposition, which says that the resulting wave at any point is the sum of the displacement of the two waves that are combined at that point. And this is often illustrated in terms of water waves, where I've got two sources of water waves, right? These two sources of water waves interfere and combine at different points, and the intensity of the wave at these points is enhanced. It gets higher. The displacement of the water gets higher, is indicated by these bright spots here, right? Because the two waves constructively interfere at certain points in the water surface. So this idea of interference with waves is historically very relevant to the discussion of wave propagation. It goes all the way back to the late 1600s, when this guy Huygens formulated his very famous principle that any wave front can be thought of as being comprised of individual wavelets, and all these wavelets interfere constructively to define a new wave front. And he applied this principle very effectively to describe what happens when, let's say, a water wave goes through a narrow channel in a wall, and then that water wave emerges as a circular wave on the other side of the wall. So he was able to explain that phenomenon as far back as as far back as the 1690s, using this concept of constructive interference. The important breakthrough with that suggested that light, visible light, was a wave, was actually achieved in 1803 by this guy Young in England. Right, Young illuminated two slits in the screen. The two slits are referred to as A and B. The two slits are separated by a distance d. He illuminated these two slits with light, and what he observed on a distant screen was a sequence of bright and dark spots, right? That could be observed if you look very carefully at the intensity of the light that struck the screen. And this sequence of light and dark bands was a puzzle, and he was able to explain it by realizing that if light were a wave, right, then it's possible that light from the top slit A can propagate to the screen and constructively interfere with light from the bottom slit B that also strikes the screen, right, provided the extra path length that the light from slit B follows is an integer number of wavelengths longer than the path length that the light from slit A follows. So we'll come back to this idea later on, but it was a very early suggestion, 1803. This is 60 years before Maxwell, right? It was a suggestion that visible light, in fact, behaves as a wave. Right? It wasn't seriously believed, but it nonetheless is there in the literature. So I think the way I like to conclude this lecture is to say that it's possible to create a table which summarizes a lot of these important results that we've discussed in this lecture. And I think the message that I want to leave you with is that by the late 1800s, virtually every aspect of electromagnetic radiation was understood, or at least it was believed it was understood. And so this kind of laid the groundwork for these novel experiments that were performed in the late 1800s. These experiments were interpreted in terms of a lot of the concepts based that I've reviewed in this lecture, and the comparison between experiment and theory failed miserably. So it's important for you to have some basic understanding of what these predictions are, so I've tried to lay those out for you, and we'll refer to those extensively in the next few lectures as we go through and describe to you some of these really amazing experiments that were done in the late 1800s. So we'll see you for that next lecture.